Hi, I am Thomas Bourgeat. Today, Jules Dréan and I are presenting CaSA, an end-to-end quantitative security analysis of randomly mapped caches. CaSA is a joint work with Jules Dréan, Yuheng Yang, Lilian Tsai, Joel Emmer, and Mengjie Yan. Let's introduce the fundamentals of cache side channels attack with a simple one-way cache composed of 4 cache lines. Let's assume that the victim application code performs a load to a specific address when a Boolean secret is 1. If an attacker can find an address that maps to the same cache line as the victim address, they can learn the value of the secret without directly accessing the secret. Indeed, the attacker can access first this crafted address, then, when the victim's code runs, if the victim secret is 0, the victim load will evict the attacker from the cache, and so when reaccessing this crafted address, the attacker will observe a slow response due to the cache miss. If the victim secret is 0, the victim won't evict the attacker, and so the attacker will not observe a slow load. Hence, depending on if a miss is observed or not, the attacker will infer that the victim's secret was 1 or 0. This standard attack is known as prime and probe. When the cache is a two-way cache, cache lines become cache sets, and an attacker will have to craft a set of 2 addresses mapping to the cache set of the victim to monitor the accesses. Fundamentally, the attacker monitors victim cache accesses through the conflicts in the cache. The set of addresses crafted by an attacker to monitor a victim address is traditionally named an eviction set. The community's intuition has been that the security of a cache can be measured by how hard it is to build an eviction set. This talk will show that this statement is not quite correct, but let's first see how this intuition shaped recent development in cache security. The first idea to make the crafting of an eviction set difficult is to hide the set index hashing functions. Instead of directly using the intermediate bits of the address as an index, one could hope that making the set index a hashing function of the address, so difficult to invert, would make the crafting of an eviction set harder. This is insufficient to achieve satisfying security. Indeed, even assuming a completely opaque mapping function, it has been shown that building an eviction set takes only a number of accesses proportional to the size of the cache. On top of this first idea, researchers looked at changing the set index function dynamically. In this technique, the hashing function is fixed for one epoch but gets changed at the end of every epoch. A common belief is that if the mapping function changes often enough, so if the length is small enough, the attack won't be completed within one epoch, so the attacker will need to restart its attack from scratch in the next epoch, because all information gathered in the first epoch would be lost. While this sounds like a reasonable belief, it is not completely correct, and my colleague will explain why later. Though it is still true that shorter the epoch is, more secure the design will be, but heavier the performance overhead will be. So on top of this idea of dynamic mapping, to allow large enough epoch while enforcing good securities, researchers introduced this idea of non-deterministic mapping function, which is as follows. To make the mapping non-deterministic, the cache is split in several subcaches. For example, in the scenario of the picture, instead of having one cache of 4 cache lines, the cache is partitioned into 2 subcaches of 2 cache lines each, where subcaches use a different set index hashing functions. So we name the subcaches hash groups. On a cache lookup, the 2 hash groups are looked up. But more interestingly, when both hash groups miss, the cache randomly picks one hash group to be filled, and the attacker does not know which hash group it picked. So it makes it harder to build an eviction set. Indeed, if we look at the victim's address, it can now map to 2 different cache lines depending on which hash group it has been mapped to. And so intuitively, we will need to guarantee eviction for both of those possible locations. The only addresses that are guaranteed to be useful are the ones that are conflicting with the victim address in all hash groups. We call them hard conflict addresses. If you can find enough such addresses, you could do a traditional attack, but the point of non-deterministic mappings is that you won't be able to find such addresses. However, we should also consider soft conflict addresses, that is, addresses that conflict with the transmitter address in at least one hash group instead of all hash groups. For sure, sometimes those addresses won't be very useful because they will not map in the useful location. Leveraging such addresses will still be useful because we can build imperfect eviction sets, that is, eviction sets that are not guaranteed to evict but that can evict. Researchers have not yet comprehensively studied all the possibilities offered by using such imperfect eviction set in an end-to-end attack. To study the probabilistic nature of communication using imperfect eviction sets, we have found it useful to leverage existing concepts from the field of telecommunication. The analogy goes as follows. The medium of communication, the cache, is composed of different subchannels, the cache lines, and the state of each cache line can be changed, we say modulated, to carry information. And similarly to the way a radio transmitter can modulate several frequencies, a transmitter set in our context can modulate several cache lines. The first part of a communication procedure is to make a receiver tuned to the transmitter. We name that the calibration step, a bit like a radio receiver gets calibrated to a specific transmitter. During calibration, one generates addresses, the receiver set, that are designed to monitor subchannels that the transmitter could modulate. In this example, one could decide to quickly craft a single soft conflict address for the receiver. But one could also decide to spend a bit more time to craft a receiver set of 2 addresses, and that would increase the probability of observing transmitter modulations. Intuitively, bigger the receiver set is, longer it will take to build it, but more accurately will it detect transmitter modulation. Now that the receiver has been calibrated, we enter the phase of signaling, that consists of acquiring samples to get the profile of the number of misses observed by the receiver. Intuitively, if the transmitter is accessed, the receiver will see misses more often than if the transmitter is not accessed. We define the signal to be the number of misses observed by the receiver, and this signal is acquired using a standard repeated prime and probe strategy similar to what was explained at the beginning of this talk. Here is an example of the mathematical representation of 2 distributions of the number of misses in case where the transmitter would be accessed or not. As the distribution of the number of misses is different for the 2 situations, we can use statistical methods on the samples we acquired during signaling to decide if it is more likely that those samples correspond to a case where a 0 or where a 1 was transmitted. We call that the decoding step, and intuitively more samples we gather, more precise our guess of the transmitted bit will be. So this end-to-end communication view highlights that there is a trade-off for the attacker between the time spent on calibration, building a good receiver, and the time spent using it to listen to the transmitter. This trade-off had not been studied yet, and we show that it can be exploited advantageously to decrease the cost of communication in the cache. To pop up a few levels, CaSA is a computer program that takes a cache configuration and scenario and outputs quantitative measure of the security of the cache. The quantitative measure of security computes the number of accesses needed to send the first bit through the side channel when using such a communication scenario we just described. In the rest of this talk, Jules will both outline how the CaSA program works and explain 2 of the many interesting properties we discovered and studied in our paper.
Thank you, Thomas. So CaSA is organized in 3 modules. Each of them models one of the 3 steps of the communication paradigm. I will now give a high-level description of the modules, but more details can be found in the paper. So first, the calibration module. Our module will simply emulate the calibration step using a cache emulator and running the calibration algorithm. It takes the cache parameters and the attack parameters as an input and outputs a subchannel mapping graph, which is a comprehensive representation of all the conflict relationships between the receiver and transmitter addresses. Next is the signaling module. The signaling module takes the subchannel mapping graph as an input and outputs the possible statistical distributions of the signal. We use a mathematical model to model the signaling step. In particular, part of the signaling step can be seen as a stochastic process and simulated by a Markov chain. Finally, the last module, decoding, takes the signal distributions as an input and outputs the number of samples required to distinguish which distribution the signal follows and extract one secret bit. That's a pure mathematical problem, and to solve it, we can leverage many statistical analysis tools to get an upper bound on the number of samples. In the paper, for instance, we use the classic result of the Chernoff bound. And now that I have introduced CaSA to you, let's jump directly to what we have found. With CaSA, we've discovered many findings that refute prior common beliefs. We picked 2 results that we will present here. So first, an interesting result is cross-epoch communication. So remember that in some recent work, the cache mapping function is changed periodically every epoch. The assumption here being that all the work done by an attacker during one epoch could not be reused for another epoch. We show that this is not true, and that information can be accumulated across epochs. Secondly, a common belief is that the best strategy for an attacker was to spend all their resources on calibration to make sure that the receiver could perfectly monitor the subchannels modulated by the transmitter. We show that this is not the best strategy, and that accumulating more samples from imperfect receivers can be more efficient to extract a secret bit. So now let's have a look at the victim code that we will use to illustrate these results. For the 2 next results, we assume the victim runs a specific implementation of RSA that specifically calls 2 functions, square and multiply. The multiply function is only called when one of the bits of the secret key is equal to 1. So the attacker tries to distinguish between the cases where the victim only executes square or is executing both square and multiply. Here, each function accesses some unique cache lines, but also executes a common subfunction that shares 10 cache lines. We use these parameters as CaSA inputs to get our two next results. First result is cross-epoch communication. Remember that in recent randomly mapped cache designs, the mapping function is dynamic and changed periodically every epoch. We consider an attack looks as follows. For each epoch, the attacker will spend part of the epoch resources to craft a receiver set, here represented in white squares, and then perform several signal transfers to accumulate samples, the yellow squares. When the epoch is changed, the old receiver cannot be used anymore, and the attacker needs to start calibrating again. A common belief is that no information can be accumulated across different epochs, and that if an attack could not be completed in one epoch, nothing harmful could happen. We show that this is not really true. Indeed, even if the attacker needs to craft a new receiver set every epoch, the intuition is that different receiver sets crafted with the same calibration algorithm, even in different epochs, correspond to similar signals, and as a result, signal samples can be gathered across epochs to decode the same secret bit. To validate this intuition, we run an experiment on our RSA example. Here on the graph we represented, the probability to observe at least one miss over various epochs for different value of the secret. So here, each dot represents a different receiver set. This is just an example that corresponds to a specific cache configuration, noted down here, victim program, the RSA algorithm, and attack parameters. We can observe that over epochs, the probabilities stay quite stable over time. As a result, we can use CaSA to compute a global distribution for the signal independently of the epoch, and accumulate signal samples over various epochs to perform decoding. So it is possible to communicate across epochs, and dynamic mapping functions are not as effective as previously thought. Let's see how cross-epoch attack performs in practice. So here, the cache configuration is the same as before. The victim also runs our RSA example. The graph represents the decode error rate as a function of the number of epochs spent on the attack. We see that in practice, communication across epochs works, as error rate decreases with the number of epochs, and the secret can be decoded with 1% error rate in less than 30 epochs. Given that an epoch unit is more or less equivalent to 100 times 16,000 last level cache accesses, we can roughly approximate the time to leak the secret bit to a few seconds. That's a lot better than the years of security promised by some of the randomly mapped cache designs. Let's now have a look at our second result using the same example. Here, we highlighted the trade-off between calibration and signaling by plotting different possibilities for resource allocation within an epoch, between calibration and signaling. We can see that in contradiction with prior beliefs, calibration is not the most important part of communication, and spending the maximum amount of resources on calibration is not always the best strategy. Here, for instance, the optimal strategy seems to be spending only 40% of the epoch on calibration, and exploit the rest to accumulate samples from the signal. So that's our last result for today, but we have many more details and other exciting results in the paper. To conclude, we really think that comprehensive security analysis for microarchitecture side channels should focus on end-to-end communication. We also think that CaSA opens the floor for statistical analysis of microarchitectural side channels, as we leverage the analogy with telecommunication to model the signal statistically. Finally, CaSA is intrinsically modular, and for future work, we would really like to extend CaSA to consider noise during the calibration step, variance across epoch, with, for instance, different epoch length, finer grained signal by, for instance, taking into account which precise subchannel is modulated, and finally, extending CaSA to work with other microarchitectural structures. So thank you all for listening, and if you are more curious, do not hesitate to read our paper.